move it one more. Hey, welcome to Coffee Compiler Club. Here today to talk about anything and everything to do with compilers and language runtimes and typing systems. And I'm going to make a go at a start at Hindley-Milner, except I didn't get very far on slides because I just started them this morning because it all blew up last night late. So I have half a slides. Otherwise, I normally have a set agenda, and you're all being recorded, and you all show up on YouTube in a few hours. And that's the end of my normal spiel. Mr. John Rubio, is there a chance I can get a 10-second intro from you? I am unclear if you have audio or a mic or anything.
Yeah, sure. Can you hear me?
Yeah.
Hi everyone. My name is John Rubio. I just finished my master's at Cornell doing a research master's, and I'm still pretty new to compilers, so I'm excited to be here today.
Cool. Okay, yeah. Anyone else want to start with anything, or I'm going to pull up? I have 10 slides, no more, and then I'm done.
Is this Henry-Milner as it appeared in the paper, or Henry-Milner improved
Hindley.
as it appears in AA?
It's Hindley, not Henry, and it's where I started from, so it's very close to the original as it shows up in like Wikipedia discussion. And you can find that starting point on a number of people's online materials. I have a different feeling for it, so I come at it from a different angle. In particular, I suck at the theory and denotational semantics, so I have concrete examples in code. And the implementation of the code I get is the starting point for what I did with AA, but AA has a lot more other things going on with it. So I'm not really doing AA because I put a bunch of extensions, but I'm taking the starting point that'll get you the basic Hindley-Milner, which will do type inference, complete type inference. And this turns out will cover things like generics. People were asking that one, but it won't. I don't have the slides to show where they show up, but you get them for free out of Hindley-Milner, although you don't get the generic names for free coming out. But the type quality you get is the same as if you had strongly typed generics. Okay, so with that, I'm going to throw slides out. And then we'll just run out of slides because I didn't have enough time. Okay, so I'm trying to put together a talk, and maybe I'll have it done in a couple weeks and can present it at a conference. And if I expand on this, I'll bring it up to CCC again. So the goal here is to get people to understand how Hindley-Milner works in intuitive ways. There's no theory here. There's no denotational semantics, and I suck at them. But I'm going to bring out some high-level ideas and marry them up with some concrete code. And I'm hoping that will give you like maybe another, if you're familiar already, this should sound familiar and maybe give you a different viewpoint. If you're not sure what Hindley-Milner is or how it works, maybe give you a good heads up or a good starting location for it. So the Wikipedia link is easy to find and it's decent. And like I said, you can find this stuff online everywhere. But they always usually start with sort of type theory and denotational semantics, and I'm just not the denotational semantics guy. So I'm just not going to have any denotational semantics, but I am hopefully going to give you an intuition on how shit works. So I'm going to start out here. I started with 3 steps and then needed a 0 step. So you get a step 0 now. Define your types. And by that, I mean, what types are you going to discover? We're doing type inference algorithm. Okay, doing type inference, what types are we going to infer on? I'm going to give you a very simple, small set of types to infer on after I screw with my Zoom windows, which are misbehaving because Zoom. Okay, that's better. So you can get a lot fancier this. This is like the simplest stuff. And most of the initial online presentations you see will stop at functions, but I'll go one more there and say structures. So let's look at this. So I need type variables. And what are type variables? Well, they're placeholders for a type that I don't know what it is yet. But I'm going to discover it because that's the point of type inference, is figure out what my types are. So I'm going to put type variables everywhere in the program. Every single program point gets a type variable. And then I will do some stuff. And in the end, I'll have only a handful of types left, and those will be the interesting types of the program, and that's my program will be well typed. or I'll discover type error along the way and say, you have a broken program. So for type variables, I'll use uppercase letters. It's kind of common in different languages. Some people use Greek alphabet and things, but I'm just uppercase. And there's some base types. And base types are things like ints and bools and floats and strings and whatever you want to declare a base type. It's a simple type. It doesn't itself internally contain any other type variables. And then there are structural types. And structural types, I'm going to say a struct or a class, by the way, is a structural type. But when I say structural type, I don't mean a class or a struct. I mean something that has some kind of structure, a box, a container, it has type variables inside of it. So a function structure, I'm going to write on the slide as a curly brace, some argument types, an arrow, a return type, and a close curly. And the curly and the arrow are the box. They are the holder, the container, and inside I have some type variables. So when I do an implementation, I say I have some kind of Java class representing my function types. It has an array of argument types and a type variable returned, or in the case of ecstasy, maybe it has an array of type returns. And when I print it, I'll print it with an open, curly and the type args arrow and a close. But that's just pretty printing. It's just a box. The box has type variables inside of it. So that same notion of it's just a box happens for structs or classes, where the box inside has field labels like name, age, salary. And then each of those is its own type variable because I don't know what type name is or salary is or whatever. I'm going to discover that as part of the program. So does that make sense? What I mean when I say, what are your types? No one says anything. I'm going to roll on as usual, and people will be confused. Okay, so that's
Can you hear me?
the end of that. Okay, so there are like 3 kind of parts here, and I ran out of slides, so we're going to stop for the 3rd key part, and that's just because I only had 2 hours to go. So that'll switch over to like live demo and discussion and no slides. So the first key part is union find. And the second key part will be unify, separate from union find. And then the third one will be type inference, and that's where I'll run out of slides. And I have more chat here. Let me go look at what's going on, make sure.
Cameron has tried to say something.
Oh, Cameron, you have no mic then. Say something.
Yeah, I don't know if my mic's
You're
working.
too quiet
Can
still,
you hear
sir.
me? Yeah. I
Better.
don't know can you hear me?
A little better, go.
So what I was hoping you could do kind of as a step -1. So tell us what the goal of Hindley-Milner is, because I mean you're diving straight into what it does and how it does it. Tell me, try to describe what it is that the algorithm does for you.
Hindley-Milner does type inference. And by that, I mean, it looks at a program and it will tell you, here are the types for every place in the program, or it'll tell you you have a type error. If it gives a type to you, your program is well typed, typically meaning that you can sort of directly convert it into some sort of running executable machine code. And you also know something about what everything is. So for instance, if Hindley-Milner tells you you have a function, you have a function, and you can call it with a machine language call instruction, and it won't crash and burn because it's not a floating point number accidentally. So it gives type inference, and it does it without type annotations. Now you can add annotations and then run Hindley-Milner first, and then confirm that what the user thinks the type should be are what the inference comes up. But Hindley-Milner himself doesn't need any type annotations to infer your types. So he's just going to look at the structure of the program.
Both to have polymorphic dispatch, so the same characters could dispatch to 2 different functions based on the type, or just to have safe dispatch to say, if you give me the wrong types, I'm not going to dispatch at all.
So kind of the answer is yes there. If you have, if you get a type error, then there's no guarantees that you can make a runnable program. And so he stops. It's just like a compiler. You run the compiler says, hey, you got a type error in your program. I'm not going to compile it. He just stops. Okay. If you want to do polymorphic dispatch, turns out that, in fact, Hindley-Milner totally supports that. But it doesn't do it in the way that you think of in the Java sense. So if you want to have like a Java virtual dispatch, you probably want to add some more. I'm going to do a very simple version. You would add more structure to both your types and your unification steps, which I'll show in a second. That would, do full-on dynamic dispatch. Yes.
I would say that polymorphism is a tangent concept to type
Yeah,
inference.
you're right. So we have to be careful here. There's two different concepts going on. The one concept is virtual dispatch, which from a Hindley-Milner point of view is strictly, I have a function variable, I'm going to call it. I better be a function. It better take the following arguments. It's going to return the following type. It's a well-typed function call. I don't know where this function came from. It's not a concrete single function. It's a function variable. Same as in C, I can throw function variables into functions into a function variable. Basically, I put code addresses into a variable. Then later I call the code address. I do a call to a hardware machine register. Right? It's not a concrete address, it's some variable. That's the normal dynamic dispatch. Totally Hindley-Milner covers that. Okay. Polymorphism is where Hindley-Milner lets you discover more fun, exciting types about the universe and allows well-typed calls to be made, and that would be kind of morally equivalent to generics. And Hindley-Milner totally does that. And I totally don't have those slides, although I was getting close to getting those slides out. Another 2 hours, I had the polymorphic slides out that had the same kind of feel here. The actual implementation of polymorphism in the presentation and the language here, or the implementation, is actually really trivial. I'll talk you through it, and then maybe we'll have time to do dynamic coding examples and explain where it shows up. I didn't have time to do it, so I'm going to get through just some stuff. And then I'll try to cover polymorphism. I should be able to get slides out in a week or 2 weeks, and then show you. But it's the same kind of feel. There's a very simple thing I'm going to do. There's a point where I'm going to say, take this type and clone it. Just make a copy of it, and that'll get you polymorphism. And that's like the entirety of the thing. We'll get there when we get there. Okay, does that cover you, Cameron? That's what Hindley-Milner is about. It's type inference.
Yep. Yeah, I'm just planning to send your video link to people, so I wanted to make sure that you covered the what it is. So
yeah, fine. Yeah, it's very raw talk here because like I said, 2 hours on these slides tops. Okay, so now I'm going to talk about building blocks. We're going to build up union find, unify, type inference, and I ran out of slides before type inference. So union find first. So what's union find? It's a well-known algorithm. It's used in a lot of places. I'm also going to use it for type inference, but it's used in a lot of other algorithms as well. So this is a generic, unrelated to types algorithm. And the concept here is I'm going to online fast find a set without knowing what the set members are to begin with. But when I'm done, I'll know the set members. Okay. When you do look at it from the typing point of view, I'm going to have every program point its own private type variable. But then I'll start saying, well, this guy has to be the same type as that guy. So I'm going to union them in the union find algorithm sense and say they both are going to be the same type when I'm done, and then in a set of types, and these sets will grow and grow and grow until I end up with your type program, which will be all these independent sets, and each set will say this point, this point, this point, this point, they're all related, they're all in the same set, they're all the same type. That's what we're going to head for. Okay, so what's union find? It's given an element, find a set, and the other piece is given two sets, union them, make them one set. Both of these operations can be done with near constant time and a tiny code, and we're going to show it in just a second. So the sets are going to be represented by a random member of the set. We're going to pick some dude in the set at random, and he's the leader. We call him, you're the set. So you look at a guy and you don't have any context, you can't tell if you're talking about the set or the member. You have to have some context to tell I'm looking at the set or a member. It's the same thing. So I have a class I'm going to define here. I'm going to say tvar is a type variable, but if you're doing other algorithms, you wouldn't call it tvar, call it whatever. It's a member, but it wants to know what set it's in. So it has a leader set, a leader member as an element. So I say tvar underscore uf, that's my union find leader, that's my set guy. Now, why underscore for me, that's personal internal syntax. It says it's a private variable. I'm not exposing it to the outside world. Might as well say private, but the slides get too big. And then I have two operations, find and union. And the find is return this dude. That's your set member, except that's not quite. That's a lie. But that's semantically, mentally what it's going to do. But we're going to have to do some complicated shit in the next slide. Not actually very complicated, but a little bit. The union, however, is legit. The union says, take these two sets and union them. What it really says is, this has to be a set leader, and this has to be a set leader. So they're two sets, not elements. And then I'm just going to take the one guy and point him at the other, and I'm done. And that single store op, that's my union. So it's really cheap to do a union. But now find gets a little wonky, because if I union this to this, I get a linked list of length 1. But if I union this into this, I get a linked list of length 2. But if I have some bigger linked lists and big linked lists, I union them again, I get longer and longer and longer and longer linked lists, and I blow my asymptotic bounds. So what I do next is a find with a path compress. And what's find really doing? Well, find says, I would normally start from my element and get my leader in one step, but maybe that guy's not actually the leader anymore. He's just been unioned into some other set. So I have to chase his. And again, recursively, no. So I follow this linked list. So here in the middle of the slide, I'm following a linked list to the end. And when I finally get to a dude who points to himself, he's the leader. Now, having found the leader, this is the value I want to return. I need to do path compress. I'm going to restart over at this and run a loop again where I follow the same linked list, but I point everyone directly to the leader. And that's what that little loop's doing. When that loop's done, everyone that I just chased all points to the same leader, and that's for your time bounds. That gets your time bounds back. And that's the entirety of find. And that code shows up in my AA and in other places where I'm doing union find algorithms. So there's a couple things to think about with find here. Find is a kind of a read barrier, where read barrier is this very generic concept. It's anything you do between you loaded up a pointer and you want to do something significant with it. So in garbage collection land, you load a pointer, the GC tells you it is or is not in the correct phase. You have to screw with it because it got moved and get the correct pointer. All kind of read barriers show up in garbage collection, but they show up, this shows up in many places. Another generic read barrier concept is, I have a thing which no one ever asks for, maybe, so I don't want to make it all the time, it's lazy. So if I pull it up and I have just a hollow box and somebody says, give me the value in it, turns out I have to go read the database for this value, and I do a one-time init and load it. But next time I pull it up, I do my check and say, oh, I've done the database read, here's your value. So that's basically read barrier notion as well. Fine. Between loading a pointer and doing something, you do a find, you do finds everywhere. That means it's easy to forget them, so it's a buggy situation. So the easy thing to do here is just assert before you do something significant that you got the leader. And in fact, while that's the code for the assert, I actually have an isLeader test I used. And then because finds show up everywhere, you want to run to fast. Turns out that the rollup case is extremely rare. And so if you unroll 1 or 2 iterations of find, you cover the 99% case without ever needing a loop. And then you move the loop off to the slow path and deal with it if it actually has to happen. Otherwise, find is generally load a field, test for self, done, and you walk away. Okay, that's union find, and that's the end of that piece. This is the break for questions. Union find's a common old algorithm. I'm not going to go. I'm going to assume there are no questions. And now I'm going to talk unify. And then we're going to run out of slides. I'm sorry. So unify is not union. Don't mix up the names. I'll use them back and forth, but I mean them unify or union, and it's easy. Okay, so unify is the type specific one. Union finds used in a lot of algorithms. So why am I unifying? Well, it's because I learned something by looking at the program, and I want to take that learning and put it into the types. So here I have a function who in green it's saying int arrow string. That means it's a function from int to string. I'm passing it in, it's an x. What the hell is the type for x? Well, it better be an int or I got a type error. So I learned something by looking at the program. I want to learn it in the types. So I'm going to unify whatever x's type is with int. And that's going to tell me that x is of type int. And then I'll recursively do that with the return from the function call. And the function itself might be created somewhere else. And I'll say, you, Mr. Function creator, better give me a function from int to string, and so on and so forth. So theory says I'll make a pass over the program, like one pass. I'll unify at every program point according to what that code is doing. And I'm done. That's it. I got my typing. It's not quite that, but it's really close to that. So let's look at unify, how it actually works. So unify is this dumbass structural recursion. So when I look at a type or two types, they're going to be the types I did in step 0. They're going to be either type variable or some structural type that I got from looking at the program. And if it's a type variable, I'll just call union on the two type variables. Literally, that's it. I'm done. Or one of them is a type variable and one's not. I'll just call it union on it and walk away. So it's not quite that trivial. If one's a type variable and one's not, union is not symmetric. The conceptual idea of union is that it's symmetric. I just have a set. I had two independent sets, a set with an A and a set with a B, and now I have a combined set AB. That's symmetric. Union, the implementation says one of them becomes the leader and the other one does not. Well, I keep the fancy one when I union here. If I have a simple type variable on my left hand and I have a complicated thing on the right, I make the simple guy point to the complicated thing and I keep the complicated thing. That's the real type. This guy was just a placeholder. He's now the same as the complicated type. So that's union. You do an if test to say, if you're simple, if they're both simple, I don't care. But if one's simple and one's complicated, I do it. The direction to keep the complicated guy. If they're both complicated, it's time to do structural recursion. And that means they better be the same type. I can't unify a function and a struct. They better both be functions, or a function and an int, right? Or a function and a float. Got to be the same type. So if they're the same type, I'm going to do unify on each of the internal parts. And then when I'm done, I will union them. And that's it. I walk away. And the union and the unify go the same direction because the union implementation is not symmetric. So I do have to pick a direction to go. But I pick the same direction and it just falls out in the obvious way you do structural recursion. You just say for both parts, unify the internal parts from left to right, and then I'm done. So here I have a structure as my example. I have a function type f. It's known to be it's a function type. Yeah, it has an argument and a return. I have some G type. It's got some argument and return. I look at them, F and G, and I say, oh, you're both function types. So you're complicated and you do structural recursion. You're the same thing. You're a function with one argument. That's okay. So we don't have a type error. Now recurse. So I take the first arguments, so which would be int and b, and I unify them because one of them type variable. The unification of the type variable is union. So I just union int and b. I have a combined int b thing, which is an int, because I keep the fancy type, not the type variable. Same thing for a and string. Unify them. One's a type variable. Just make it a union to the other guy. It's a string. It's an a string combo. That means my in type is f and g as the combined set. They're the same type. Is a function of int to string. And everyone's just when I put the slashes in there to hint that they're all smushed together. Really, f and g lose their separate identities and they become members of the fg set. And int and b lose their separate identities and they become members of the int b set. And I keep the fancier part and I throw the type variable part off to the side and don't pay attention to it anymore. And that is unify. And it's like stupidly easy.
Maybe one quick comment on terminology. The reason it's often called union is because we think of those as sets of constraints. So you may have one set of constraints that the variable I has type A, and you don't know A yet. And then you have another constraint that you add an integer to the variable I. And if you unify those two sets of constraints, then you have, okay, variable I has to have type int. So that's why it's called a union. It's basically your union set of constraints, or you are doing constraint solving.
I don't think of it that way. I certainly see people present it that way. I do think of it as union from the union find algorithm. I'm unioning two sets, which could be type constraints. They are types. So yeah, you can think of it as constraints. Okay. Like I said, I don't think of it that way.
Right. I mean, literally depends on what type system you have. If you can still use union find, then it's gonna be the fast algorithm. But if you sometimes generalize or you have a dependent type system, You may have
Yes.
to do some more work. So constraint solving is just more general
Yeah,
term.
constraint solving solves a different set of things, a sometimes more powerful set of things.
I would just say that union find is a one particular constraint solving algorithm here.
There you go.
It's a
Okay.
special case.
Yes. So like system F won't work this way. But you can go long ways. And of course, many of the well-known functional typing languages start with Hindley-Milner and go quite far. That you don't need too much more. You can do more. It's not, you can get a good spec for a language that has type inference with just Hindley-Milner. Okay, then I ran out of slides. And now I have to go, break. So this is a good time for questions, and then I'll try to pull up code examples. And I have some code examples, and I have running things I can run on the code examples. And then I'm not set up to run on them at the moment, but I'll be set up in like 5 minutes. So I'm going to quit the share, let people talk. I'm going to push up a code example, and we'll switch to what it means to walk the program. The slide's correct. You're going to walk the program, and you're going to unify as needed. Commonly done in one pass or an AST, which is what I'll present in my online thing. But you can do it in any order. There's a bunch of things you can do like free there. And then you do things in the order. You do things in the walk that you look at the program and say, oh, it's this kind of a program thing. So I need to do that kind of step. In that step will be unifies of various kinds. I'll be making types or unifying them with types I've already made. And when I'm done, I will have completed, I will tell you what the type of the program is. So done with that, and I will go try to kick up a presentation example. And that will take a minute to get going here. And IntelliJ is still loading. Not too surprising.
So what do you think is the minimum that's required to get some polymorphism going? Because it's something that I'd like to do to some extent, but I don't want to do don't want to do anything fancier than I need to.
Right. So what I've said so far, plus there comes a point in the program where you're going to clone one of your type structures. That cloned type structure is where you're going to get polymorphism from. And in the literature, it's sometimes called making a fresh copy of the type. You'll see that term show up in different places. A couple of different terms people use, but it's the same thing. In the end, you reach a point where you've got a well-defined type variable and you want to use it in different contexts where you want to say different types. So the common thing is I have a map. The map takes a function from A to B, and it takes a collection of A's and it turns a collection of B's. Well, what's A and B? Well, and every time I use a map, it's a different type. So map is polymorphic. And that means the type I described, just a second, Theodore. The type I just described, map, is a function which takes a function from A to B, and a collection of A's gets B's. Okay, those A's and B's will get instantiated at each point where I use map. And that instantiation at each point is where you make a copy of the A is a collection from A to B and A's and B's collections. You make a copy of that type, and then it begins to unify with its local context and discovers that, oh, you're talking about a function from ints to strings. I need a collection of ints. I'll get a collection of strings or whatever it's going to be. So the key piece you need is to clone a type, and then where do you clone the type? All right. Yeah. Maybe I'm getting to where I can do examples here.
One key and tricky thing is how Hindley-Milner decides that a type is polymorphic.
Yeah, well, that would be how, and it's not terribly tricky in the AST land, and in AA where I do it with SSA form, it's only a tiny bit more tricky, mostly because because the cognitive disconnect between ASTs and SSA. I am trying to get my IntelliJ up for a presentation. It's got tiny fonts and big screens and things. I'm still screwing with it here. we'll just do a standard zoom.
You can always share just the portion of the screen where it is.
Yeah, and then the windows get off and stuff. I'm getting there. I'm going to attempt to shrinkify a bunch of things. And IntelliJ's got its mindless thing it does that's broken since the last update that causes it to open 1,000 tabs of things that I never asked for and never want and don't want to look at. And why did you open this tab? That's very annoying. So I have to close all the bonus tabs so I can shrink one of my 3 windows. So I only have 2. And then I can shrink the whole thing. And now the windows aren't crushed to death. And let me get rid of a few more tabs so I don't have tabs running off. So one thing about Emacs, the count of tabs is not held on the screen. They're 1, 2 buttons away, but they're not held on the screen. They don't. I always in Emacs I'll have 100 tabs open, and IntelliJ that would just scroll off your usable area with tabs. All right, what am I doing here? I am attempting. Oh, I need to get a. Either I probably want to do this with just IntelliJ. It's gonna suck. What am I doing here? I want a file. I want a test basic 11. Oh, yeah, here we go. Okay, let me get a simpler one. Let's start with this. Okay. Now I'm going to attempt to share, and we're going to screw around a bit while I'm setting up. So, life sucks while I get it figured out here. Hopefully that's readable.
Yes.
Yeah, okay. And now see if I can actually run something. He's hiding my run things. And let's see if this just does the right answer. And it didn't because I haven't cleaned these things up since forever. It's fine. Okay. Really? Why are you? Okay, fine. So here's the program. It consists of the number 3. And the interesting type I'm looking for here is the number 3. And why did you? It should have given me a number 3 out for the answer. So as a AST, let me start you with an AST presentation view. Where am I going to get that from here? You're going to get it from, yeah, Rocky Start is the usual thing. I don't have, this is the old stuff that's simpler, and I don't have it up and running in the guy here, prep tree, and you do your shit. Here, what happens? Okay, yeah, okay, so I have a root, and it consists of a program that has a 3. It's very, very, very dumb program, very simple program. The program consists of a constant 3. Constant 3s always unify with, well, with integers or whatever it's going to be. So if over here in my implementation, hello, double shift, double tab, let's see here, going to be con says somewhere in the world, I'm going to do, where's his prep all does it from one go. His type variable is simply the constant, which is 3, and from the float type to the HMT type. So his type variable is just given to you as an int directly. So 3 is a really dumb program to go do, and that's the reason I picked it. So let me go look at, I don't know what other I have in here. A lot of these, I don't know what they are because it's hard to explore with this guy. Let's go pick, well, where'd like 2 and 4 go? Why is it not listing them? Math rand is 2 or 3, is 3 or 4. Okay, what's this guy look like? Test exe, 4, run it again. Okay, boom, I get an AST out. Here's my root. I'm printing the AST. The AST consists of an apply. Did I get 4 correctly here? Make sure I picked 4. Why are you doing it this way? I ran exe. Oh, which one? Hang on. Wrong 4. Okay, this 4. Pair. Very stupid. Okay, pair just says, make a tuple of 3 and 4. I have extra stuff because I'm doing other fun things, but the top level root is, I don't know if you read here, exe$apply is the apply function. I'm applying a function. There's a function argument. Under fun is equal to the function I get from whatever this expression is. Turns out that's a primitive pair. Pair is a function. Okay, I have some arguments. There's some extras we're going to ignore. And I have a 3 and a 4 as my actual real arguments that I'm passing to pair. So when I go type this thing, I'm going to type pair as a function that takes 2 arguments, takes a third extra argument, the $dime, which we're going to ignore. And it's going to return me a pair type, which is a form of a structure. So I got a pair out, a tuple of 3 and 4. And when I do type inference here, prep tree, I run my things, I'm a little fancier, and then I have bug checking, which I don't care for. So somewhere in here now, I have given myself types. I have some type variables. Oh God, I'd give you the fancy version still, sorry. Type variable, what is this type variable? Well, it's a pointer to a tuple because I'm expressly doing memory. I give it an alias for whatever I got. It's a pointer to. What's a pointer to? It's a pointer to a struct. So here's TV struct. That's my type variable, struct. Struct has 3 fields. I'm going to ignore the class pointer, the field or 0 and 1, and a hat. The hat's Java class field, Java mark class fields. We're going to ignore that. And it has 2 internal types. So here's the pointer to your class, ignoring it. Here is this leaf with this funny printout. What the hell's going on there? Well, the leaf is himself was a type variable. So I say TV leaf, that's a type variable directly. It has a UF field. This leaf has been unioned, and the double arrows on my printout that I'm highlighting, that means I have a union step that happened. I have not done a find, which will roll it up. So the debug printer keeps the finds not yet rolled up. So I have a type variable. Type variable is x506. It's X because it's been rolled up or it's been unified, and it unifies to some pointer. The pointer is to an expanded fancy. It's a boxed integer. It's a capital I integer Java 3. And I look at my other result for this tuple, and it's the same thing. It's a boxed version of a 4. So when I look at the program that I started with here, this apply of a function call to a pair with a 3 and a 4, I made a function type that took 2 arguments, but I didn't know what they were. Left them as type variables. And then I unified them with 3 and 4. And so I get this unified version of the answer. So this program is well typed as returning you a pointed to a tuple of a 3 and a 4. All right, let's go find fancier things. And this guy sucks for exploring my file system. So let me go explore it with Emacs, because I'll find some fancier types here in a second. And I went exe, and I want, let's see, I did 4. Let's see, what does 5 do? Nah, that's fetching a field out. Here's first step of let polymorphism. Here's an if. Here's another if. Let's take this guy. What's this one? This is 8. Okay. Actually, in exe. Yeah. So here is a function. So open curly. It takes an argument p. It's this arrow. Then what are you going to do with it? You have a body. The body is if p is true, I'm going to take a 4. Else I'm going to take a 5. So this is a function that takes an argument and returns me either 4 or 5. And my little comments up here tell me what types I go look for when I run it through the tester. And the evaluation is a little fancier, but what it basically says is it's returning me a function. So if I just evaluate this expression, I'm not applying this function on anything. It's just a function. So I get a function type back, which I don't print the details in the evaluator, but I'm going to show you here. Okay. Here's my AST. It's all run off to the right here. It's just highlighted there. It's a function. It's function number 3. That's the 3. It takes a class pointer, which I'm ignoring. It takes a dying field, which I'm ignoring. Those are part of my fancy stuff for AA. It takes a P, which is my predicate. It does an if, tests the predicate, does 4, 5. When I look at this thing as an AST here, I'm staring at my AST. I'm going to start breaking down the parts. I have the program is this lambda. I break into a lambda. Lambda has some args, and those are just names. So P is the last arg, and there's a bunch of other ones, and the nulls are just to align my arguments with my parts list. And I have a body. The body is an if. If has a predicate, which itself has a body, which in this case is a single identifier P. And it has a true side and a false side, which are 4 and 5. So I have an AST, an abstract syntax tree. And when I walk the abstract syntax tree, I do my unification steps piece by piece. So I said unify a constant, it's just its type. If I look at the unification for if here, it's going to say, go do my parts in this is the early unification piece. It's just this is my fancy algorithm done to simple parts. I don't need to go to the other parts because it's too simple here, but it's basically go all the parts and do what you do with them, and then go look at the thing I got. And if I got some kind of constant, I'm going to do a fancy guy where I'm going to decide I'm unifying just the left or just the right. I'm just true or just false. And if it's none of the above, I'm going to have to unify the result. That's TVAR open close. That's my find call with the true side. And if your comp here is, possibly the other direction, you're going to unify with the false side. So basically, if says result of the whole if expression is either the true or it's the false or it's the unification of them both. It depends on whether I can do some constant finding on the predicate value. The constant finding is fancy for AA. The standard online materials you'll find won't do anything here. They'll say an if always claims that the result is the unification of the left and the right. And furthermore, actually, the predicate usually unifies with Boolean. For me, my predicate has to be a base for me to do anything fancy with it. And if it's not, then I don't care. I'm going to evaluate it, and I'll take my ifs, take anything, and they'll do a null check on anything. So it doesn't have to be a Boolean. Yeah. So I don't have a test for Boolean here or a unification of Boolean here, which other folks would. And instead, I'm also optionally unifying left or right according to whether I discover something. So that's the AST I have. I go run the unification algorithm step here. I get a type variable out. The type variable is a TV lambda type. I have a function. The program is typed as a function. It has some args. In my case, it has 5 args, of which the first 4 don't count because they're part of the AA thing. So here's my 5 args. The don't count one and the no don't count one. And the actual leaf is the one that counts. The output is in slot 0 here. That's the result. And the result says, oh, I'm a boxed integer of an int 8. I happen to know that you're going to be a non-zero 8-byte result. But I don't put any predicate. I don't put any type constraints on the predicate because in this particular unification algorithm, the predicates on an if can be anything. So there's no requirement for it to be a Boolean here. Okay. Let me go find. I'm gonna get one more fancy, and then I'm gonna jump to a lot fancy, I think. That's not terribly exciting. That's float testing. That's interesting, but only a little bit. A lot of these are me testing primitives, so not very exciting. I did the same thing with 4 and 5 I did with strings, for instance. Randomly pick left string, right string. Yeah, that's not terribly exciting either. I could pull it up. One more unexciting one. Yeah, okay, I'll pull one more unexciting one up here, and then I'll break out into excitement. Okay, rand is a built-in primitive, so ignore equals call rand. So call random number generator, because actually I wanted a different thing out. Then use the random number generator to pick one of these two expressions on the left and the right. The pound sign is string length. So this says call string length on what better be a string argument. I have two constant strings here. So I'm just going to get two constant strings. I happen to know what the random number generator generates. So the evaluation of this is false here. This RN rand, the second one reports false. So I evaluate this, which gives me the length of the 5 length string. So I get 5 out. So my eval value is 5. Okay. Let me run that. And here I have my tree, and it's scrolling off. So it says, in one long line, ignore equals random of, ignore the dying thing, that's my AA thing. There's a semicolon, then if random question mark, apply length to ABC or apply length to DEF. So I don't have a tree pretty printer, it's all in one long line. There it is. Let's go get the type. Type says N64. Okay, that was correct and very uninformative. Can I do better? What can I say here? Well, it turns out if I go to my types in my tree here, I have them layer by layer. So the program has it starts with a let expression, which is how you define a variable in Hindley-Milner. Let x equals some definition in the rest of the thing. For me, my syntax is variable equals definition, semicolon, in rest of thing. So I have a let expression, but the top level let expression is the result of the whole thing, including the body at the end, which means it's an int64 type. But I can break down the parts here. So I'm defining ignore, the variable called ignore, by applying a random number generator. So look at apply, applies in a call site. Apply is basically a call site. I'm calling a function. The function is random. And I'm going to ignore my args. Their first 4 leading args are all the ignored things. And it's going to return me some int64. Random gives me an int number. Fine. So that's all well typed. To go function here, his type is, oh, geez, a bunch of complicated things. I'm going to ignore all those args and returns me an int64 at the end. So if I look at the expression as it rolls across the screen, the very end says arrow a colon n64. That same a64 shows up in other places, but it's just an int. Random returns me an int. Done. Okay. The body of the let, the thing that I do with ignore, which I don't do anything with ignore, is if random of do things. So if it has a predicate, which is random, what's the type of predicate? I'm going to drill in n64. Oh, you call the random number generator, you got an int back. Fine. What's the true side? Well, it's an apply of a length of a string of whatever it's going to be. If I drill in, it's an n64. And that's because it calls length and with an argument, which is a string. And length himself is a function which a bunch of random stuff in the beginning is leading args, I don't care. Right at the end, string arrow n64. Takes a string, returns the length. So that's sort of how you're breaking these things down without getting fancy there. And this is a good time to say something before I pull up like fancier stuff. Like I'm going to pull factorial up in a minute, and that's going to break open a bunch of things. No one said anything, so everyone's either asleep at the wheel or we're all waiting for factorial. This is a better factorial. We're all waiting for factorial. Everyone knows what factorial is here. Okay, what is factorial? Factorial, I'm going to read this is my simply typed lambda calculus syntax, but you could write the same code in C or Java just almost the same way. A little bit of syntax change, a little syntactic sugar, same code. Factorial is, well, it's a function. That's the open curly. Takes one arg in. What's it do with that arg? Well, it tests it for 0. And if it's 0, I'm going to return a 1. But if it's not 0, I'm doing this, which is the obvious factorial. I'm going to multiply n times whatever you get out of calling factorial again with subtract of n and 1. And that's factorial. And then I call factorial with a 3. So this is a much bigger program. So let's go see if I can talk it through. Just do this. So first things up, I have an abstract syntax tree.
How do you get away with without declaring the letrec, the factorial, to tell it to use
Okay,
it?
right. So this is this that equals, that is my mutual letrec. Okay, so this is always a and I don't have more than one thing, so it's just a letrec here.
So
and because letrec and let are exactly functionally equivalent, only depends on whether or not you include a recursive or not. I can implement the same ways. It's the same exact code. There's no change to the code. I call it let in this particular code base, but it's a letrec. And that's it. This is the keyword let. Let fact equal blah 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 in blah blah blah. Like you're missing here the let keyword, and this is in, but that's just syntactic sugar, so I don't do that.
Yeah, but because there was some distinction that has to be made.
Yeah, this is where it gets ugly. This is where you get polymorphism from, which I haven't talked about, and I didn't have slides for, and so I was just, we're getting to the sort of the heart of the gruesome meat of the fact here. So when you look at this kind of expression here, you find these identifiers like fact and in floating around, fact and in floating around. And the behavior of them varies according to where they came from in one important way, and that's whether or not it's let polymorphism or not. So let polymorphism is where you get to reuse map call with function from A to B, and a collection of A's make a collection of B's in all these different contexts, and the A's and the B's change according to context. And that happens when you're using a defined value in its use, not in its definition. So here I have highlighted fact where I'm using factorial. This point will be let polymorphism enabled. I would use let polymorphism here. And here I would take whatever type there is for fact, and I would say, make a clone of it. Now with that clone, now infer the rest of the expression fact of 3 and tell me what your type is.
Okay, so now what is the n of the definition?
Yeah, let's go. So fact is defined here. In, like this use of in is defined here in a lambda as an argument. You don't do let polymorphism. This fact is used inside the definition of fact. You don't use let polymorphism. This fact is outside the definition. You do. That's the entire distinction. You crawl the AST from bottom to top. If you find that you're crawling up into the definition, you don't do polymorphism. If you're fine or crawling up through the body, you do. And I have that crawl in the code, and I can show you where it happens. And that one, and exactly that point, I'll say you're fresh or you're not. And if you're fresh, I make a fresh copy of the type. And if you're not, I don't. So this in is an identifier that's defined by the lambda. Don't do it. This in, all defined by the lambda, don't do it. This in is defined by the lambda. It itself doesn't have, it's not a use of an identifier. It's just a name. And the lambda will put a type there that I'm trying to discover the type for in, but it's just a name in the program text.
It will be a type variable until you reach the end of.
And well, when I start unifying in with other things, I'll discover, it's a type variable until it gets unified.
Will pick up constraints, for example, the multiplier. So how do you record that? Okay,
so for me, in this program, it's not AA anymore. It's just simple stuff. It's a standard multiply. In this case, it's integers only. So as soon as I say I have a multiply, it's a function that takes 2 ints, returns an int. That will force in to unify to an int. That will force the return of fact to unify as an int. Same for subtract. Int has to be, in has to be an int. 1 has to be an int. Okay, one's an int, and done. Since multiply returns me an int, and one is an int, the if returns an int. And the whole thing obviously is just going to return me an int. Yeah.
This is simple, okay?
Yeah. This is the whole point of this is I'm showing you some
So
polymorphism, some recursion, but it's
one
still
comment here is that exactly the strength of the Hindley-Milner and the weakness of the Hindley-Milner is its strength, because once you equate something, you throw away it and you just treat it as what you equated. So you don't record anything else. You don't record that it has to be.
I just showed you last go around. I record every element, every type at every point in the syntax tree. I do record them.
When you do unification, you just say one thing is exactly as the other thing. It's not less, it's not more.
That's
I'm
correct.
hinting the fact that it doesn't support least upper bound and of such, so it doesn't in itself support subtype.
This is also why you can use union find, because you are doing equality based unification.
Correct. That is correct. That's why it's its strength. Yeah.
It is incomparable to the standard data flow analysis techniques. That is, it finds things they do not, they find things it does not. So the two discover unrelated sets of facts. Mostly Hindley-Milner discovers relationships between program points, and data flow analysis discovers facts about a program point.
Yeah, that's my comment before, was that once you discover that the multiplier has to be an integer, and the unification does it, it has to become an integer. It doesn't become at least an integer, or at most
Right.
something
it doesn't
else.
Become a positive integer or a negative integer or whatever.
So it doesn't say that it has to be a subclass of integer. It doesn't say anything of that. The unification say it has to be exactly integer.
Yes.
And
now I've done extensions in this very code base, which we just saw in the very last example, where I do track that you're just using subclassing, and I will track some amount of subclassing. So that gave you a non-zero integer 8 in the last example. That was an example where I said 4 is a non-zero integer 8. 5 is as well. When I unify 4 and 5, instead of going to int and giving it up, I said, oh, you're a non-zero small integer. So I definitely can, you can do more things with Hindley-Milner. I'm presenting the simplest stuff. It is not comparable with data flow analysis in general. That example I just gave with the 4 and 5, it doesn't do other things that the standard data flow analysis does. And the big project I'm doing with AA is unifying those two typing frameworks so I get the strength of them both at the same time. And part of that would be that if statement where I said, if the flow side tells me that you're always null, or you're always not a null, or you're always 0, or you're always not a 0, I don't have to unify the other side. And that means that I don't force a new constraint in, and I get a better answer. I get a sharper answer. So, and I have examples where those make a difference. And do they make a difference in large programs? I have no idea. Okay.
Let's throw on.
Yeah. So I'm going to push on, but this is exactly the time to stop and ask questions. This is like great stuff. I have the AST not pretty printed in a nice way. I'm going to read it from left to right. The root says I have a let factorial is defined to be function number 5. It has a hat and a dine argument. I'm ignoring it.
There is a question in the chat from Anas. I will read it. How does Hindley-Milner tackle the subtyping classes if a function takes in a type T, but a subtype S is provided where S is subtype of T?
Okay, I have to go pull up the chat because that's too
abstract.
Much here. Yeah, no problem. Yeah. So it does, and I'm not quite there. That the whole point of map is that you pass it things that are essentially subtypes left and right, and you get an answer out. So it does and it doesn't. It does non-trivially. Like I'm sorry, I'm not ready to say that. I have, I want to say textual only extensions, syntactic sugar extensions that will give you the effect that you're looking for. And then that's exactly one of my goals with AA, is totally to have a subtyping relationship with Hindley-Milner doing inferencing. And it's really syntactic sugar. Now, it's a little subtle, and so it becomes like obnoxious to look at. And it'd be nice if I had slides that showed you how you got there. But I'm going to add things to your classes. You have class S and T, and you say subtyping. Let's go ahead and change those to being some Java class S and some Java class T, but you can get more generic things, some structure type and some other structure and one subclassing. But what's subclassing mean here? So I'm going to say one has more fields and functions than the other. And so wherever you're using the subset fields, you can use the greater guy with the extra bits, and he'll be fine because you're only using the subset that are common. Hindley-Milner will totally do that. Now, can I make it look like a subtyping? Yeah, but I want to add some syntactic sugar so that you said, oh, I have a person, then I have an employee, which is a subtype of person. And then I wanted to inherit those fields. Hindley-Milner essentially does duck typing everywhere. And if you work with duck typing, you're good. But then you can force duck typing to be nominative by adding custom special fields, that's my syntactic sugar, that you must match on the names on, and suddenly you get nominative typing as a subclass of duck typing. So Hindley-Milner does infinite duck typing everywhere. And if you can then constrain it to be subtyping in the classic subtyping sense. So does that answer you? Is it Manas was asking that? I thought you were saying Yasser. It was Manas. Okay. So I don't have those examples lying around, but maybe a week or 2 weeks I'll have improved slides and I can show those. Okay. People want me to carry on factorial. It does the obvious thing. Or are we good? Do I want to pull up another example here? I have this map example. Maybe it gets closer to what things you're looking at. In the absence of comments, I'm going to help to read out this line. It just says what you think it says. Then I can break it down. Let's go ahead and type it. Oh, you know what I should do? Is I should show you where that code is. And yeah, there's the type error because I had hacked other things. Cannot unify. Yeah, okay, fine. That's me not updating my exe examples. I should switch to I have a more complicated one that this is all set for. Fine. Let instead me talk about what's going on here with identifiers, because this is the key piece that people you're asking about. So somewhere in the universe, I start by calling walk my AST and do something. And the walk the AST is looking for, going down is looking for every structure and calling prep tree, which is where I do my first step unification. Might as well call it unify here. Prep tree might as well call, walk the tree and unify. When I get to an identifier, I have to ask this question. Is this identifier defined in a lambda arg or a let definition, or I'm in a let body? So I walk the parent linked list. I have my parents, I walk them up one after another, pointing to environment, walk, 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 walk. And when I pop out the top, I'm going to ask a question. Is fresh when I find the correct point where you're defined. And what's is fresh doing? He says, oh God, start with your parent. This is the walk. Sorry, that wasn't the, this is me breaking down parts internally. This is the walk in question, which is start at your parent, set your prior to this. So I have two pieces. I have a bottom piece, this, which is prior, and a top guy, which is sin. So I syntax tree element, and I'm walking them in parallel. One's just trailing behind the other. And I go ask the question, is the guy I ran into a lambda and your name is in the argument list for the lambda? If so, you're a lambda argument, you're not fresh, done. If I walked out the top for root, it's not true, but there's a special hook for the dining field, which doesn't relate to here because that's my extensions for AA. If I find a let and the let is defining your name, oh, maybe you're being defined in the body or in the definition. Now I go ask the prior guy, are you the body? If you're the body, then I have to deal. And this is returning true or false for fresh or not. And then there is a throw if it turns out you're a cyclic reference to a struct type, which doesn't need to matter here. And then you can be other types, which I typically just roll through. So this code is a little more complicated than what I'm stating because it does other things. But the essential of it is walk the AST parent by parent and find out if I walked into the def or walked into the body of the let. And if I walked into the body, you're fresh. And if not, you're not. Okay, what does fresh do? So I make a fresh copy. It's arg.fresh. What does fresh do? It makes a copy. Okay, there's a non-gen thing I'm not going to talk about right now because that gets into recursively the nested copies of fresh things you're inside of, which makes the fresh not quite a true clone. It's almost a clone. Here's my implementation of fresh, make a fresh copy. This messes up the clone. I am going to talk about it because I'm here. I set some shit up so I don't have to have these variables passed into the recursive fresh every time. And I call under fresh. So these are global variables, just so I don't have to pass 27 arguments into fresh. Fresh has that assert I talk about all the time where you have to have a find. And if you fail to, you'll screw yourself up. So you're not unified. You're not mid-find. There's a cyclic case that I'm going to handle that most other algorithms give up on and say, we don't do this. It's sometimes called an occurs check. If this type occurs in that type, we give up and we say we can't handle it. I handle it. That gives you a cyclic type. In my implementation, I have to have a leading check before I go into the depths so I don't have a cycle. That's what the vget is doing here. If I get an answer out, that's my answer. That's my cycle. I've closed it. The non-generative set, non-gen, that's where you have multiple recursive definitions are inside of. That one needs slides. I don't want to go to it right now. It just, if you hit this, I'm going to put you in my cycle checker and get out. Otherwise, I call copy. Copy's a dumb, shallow clone. I have some stuff for doing this incrementally, which doesn't apply in the standard algorithm, so you can ignore that one. I stop you in my cycle, same as up here. Again, you don't do cycles, you don't have to do this one. Now I do the recursion. If you have some arguments, for the arguments, if the argument's not null, call under fresh on the argument and collect them all in this T that I'm busy making as a copy. So T is shallow, dumb copy, and then I fill in the recursive parts. That's the algorithm. That's a deep copy of a clone of a possibly cyclic algorithm, a possibly cyclic type. If it's not cyclic, you would do a deep copy checking for sharing. You have a bit vector for sharing. I'm using a hash table for sharing because I have cycles, but I would use a bit vector here for sharing if I didn't. So you make a deep copy. So getting back to what was going on in the prep tree, I make a copy. That's my copy. And then I'm done with that, or it's not a copy. I'd either take the thing as it is, or I get it as a copy. Yeah. That's it. So that's kind of the whole algorithm. I don't have the simplest version because I kept doing extensions and testing them. But basically, the concept is you walk your AST. If you're an if, you have a particular shape of things you do. If you're a lambda, you have a different shape. If you're a let, you have a different shape. So here's a lambda. What's lambda doing? He says, my type is always a lambda type, so type variable lambda, with the return is a leaf. And for me, I'm just going to say how many args I have. And then I'll fill in the args by walking them and putting in whatever argument type I got. And that one turns into, oh, why am I putting the struct pointer here? Oh, this is me putting in the class. You can ignore that one. That's the, the standard algorithm doesn't need the class pointer. And then when I'm done with doing the arguments, I'm going to call the body and recursively do it. Non-gen push and pop is exactly me saying lambda args do not do fresh things. So I push them on the list beforehand. I pop them when you're done. And then the last thing I do is I say myself, which must be a TV lambda. I have to be a function type. I have a return. Whatever return type is, it has to unify with the body that I just did. So you get one pass, and lambdas do this thing where they say, I am a function type, I have some args in return. When I walk the body, I unify my return with the body. When I walk the body, all my arguments are available to the body, but they're all plain variables, and the body will put constraints on them. Here's a function call, apply. Function call says the result is a leaf. I don't know what a result is. Apply. The function call returns something. I don't know what. Oh, I better go unify walk AST of my function. Now my function came back, and it better freaking be a lambda. It might be a leaf if there are no constraints put on it, but it better be a lambda. So I'll make it a lambda, which takes some args and returns an unknown thing. And it returns myself. The result of the call is what the lambda had better return. And then I'll force a unify if you weren't already a lambda. If I had to make you, if you were a leaf, then I unify you to this lambda. You're a lambda now. Okay. Now that you're lambda, I'm going to walk all your arguments, and the arguments as functions, as complete expression trees. I get their type, and I say the type of the lambda has to be the type that I got when I evaluated for the argument. The call's passing in. Basically, the function takes an argument of a certain type. The call argument is of a certain type. They better be the same type. I'm calling a function from int to string. I better be passing it an int. So I'm going to unify and force. And again, with the return, the result of the call is whatever the lambda's result is. So I'm going to unify them. So this sort of structural thing you do when you walk the whole AST, each of the different parts has something uniquely different they do, but it's all kind of straightforward. Structures, probably I have structures in here, I bet you. There's if. I guess I talked if before. Here's let. Here's struct. Struct says, oh, my type variable is a pointer to a struct, which has a collection of labels as fields. And each field is, I'm going to walk and do my prep to in each field in turn. And I'm going to unify the structure field with whatever the expression that initializes the structure is. So that's a struct. It's a collection of things. Each one individually has been computed using an AST walk. That's the type you get for the structure type. And then field does the obvious other thing. I don't know what my field is going to load, but I do know that my input had better be a pointer to a struct. And if it's not, I'm going to freaking unify it to a pointer to a struct that has the label. Right here, my pointer, my input pointer had better be a TV pointer, which is a type struct, which better have a label of the label I'm looking for, and it's going to have whatever type that I'm in. And then I'm going to unify those. I'm going to demand your pointer, you better have this field, and this field has to have the type that I load. And if it doesn't, by the way, then I'm going to throw up on you and say, hey, you have a struct without a field, no, missing a field. So you get an illegal argument there if you don't have that field. So what else things? Unify can throw errors at you if you have the wrong structure types. Somebody wanted a function, you passed them an int. Unify will say, I'm unifying an int and a function. That's an error. In my case, I'll do something with the error and report it later. In most common algorithms, I just blow up on the spot and say, done, you got an error, you're out of here. I think everything else gets into primitives now. Dynamics fields, that's my field overload extensions. Roots more or less just ask what the expression does, and my type for root, t-bar, is equal to whatever the program's type variable is. That's pretty easy. T-bar is call find on a type variable. And then if it changed, update it. Update yourself. That's the find step done one step for just the local types here. Otherwise, it's just a find call on a type variable. All right. I've talked a long time. No one said anything for a long time, so I'm probably talking to the wall. I got to be done.
And we are listening. So
It was followed.
Yeah.
Good. This is no comments, so I'm getting worried there. So it's a good time for questions, and I can share again if it makes sense. Nothing. Excellent.
we can go to the polymorphic example of map.
You want to do polymorphism? You want to get brutal on yourself? Yeah,
Okay.
we'll try it. No slides. It's ugly. I go find one here that's good.
Yeah.
Oh, recur 3. It's another fancier one. Oh, there's a brutal one. That's closures. No. That's more closures. I know I have a map call one. Oh, here. Geez. Here I have a Newton's method. I'm solving square root of, and I type it. Interesting. I didn't realize I'd forgotten, I guess. Now here's even and odd. That's your mutual let rec example, is the even odd example. Where's me wrapping ints? I thought I had a map call, a classic map. Here is one. Is this really polymorphic? Well,
So for now, only functions can be polymorphic. The structures can
my structures are polymorphic too. Yeah.
Okay.
But that's standard Hindley-Milner structure extensions. People who do, you find this in the literature. I didn't do anything fancy there.
Yes.
Do I not have an obvious map call? What did I put it under another name? Oh, grep map.
So when you do Henry-Milner, you usually expand integers till you get to some size and then just stop.
When I do Hindley-Milner, I usually do what? Expand?
Yeah, if I have x equals x plus 1, that's going to blow up to be an int64.
Yeah, there's no expansion. Yes, so the classic Hindley-Milner says plus demands an int and an int returns an int. In one step, you go straight to an int, a full int64. Okay, my versions have a couple layers, but the layers go pretty quick, and add is not smart. So he takes the two input types and takes the bigger of them both. He takes them both, takes the bigger, and goes one bigger because you added it might overflow.
Right. So it's less of a Henry-Milner question than a language design question of, do you want it to blow up at you and be like, hey, this is a thing that has a potential overflow. You need to have code that has a try and a catch and handles the overflow, or
so that's a language
compile
design.
For you.
Right, it's a language design. If you go old school Hindley-Milner, people just say int. They meant internally int32, whatever the max int was at that time. Sort of more modern folks say, no, we love our big integers, and they flip to big integer man. Then you get big integers everywhere, and your performance sucks. Then they try to get fancy under the hood and say, well, I'm not going to expose to the end user, but I'll try to keep you in an int 32 or int 31, and I'll do tag bit testing. And if I tag bit set, you're an int 63. And if you go to int 64, I follow the tag bit. These are why you have tag bits.
Maybe the appropriate way to say, I don't want to pay the cost of big integer is to handle the overflow.
Yeah, so you could say I have two types. I have an int primitive that does 2's complement overflowing integer math, and I have a big integer version. And then if the twain meet, you always default to big integer. But if they don't, you're doing 2's complement overflowing, non-checking. Now, if you want to also have, say,
but you could totally have the compiler trying to give you the safety of you have to have handled what you want to do with wraparound.
Right.
So if I'm adding a bunch of numbers, I need to say it's a wrapping add, or I need to handle the overflow.
Right. And people do those languages, and they suck to write code in because you end up with wrapping tests everywhere. Or, and all these useless, stupid places where you know you're only adding +1, and the compiler has no clue. You're adding +1 to what? I don't know. So he has to say, put a check in, and you have checks everywhere. And now you're back to huge annotation counts, pain in the butt, or the compiler put the tests in, which meant that you're just the same as the guys doing tagged integer arithmetic. Or you did the overflow and you blew it off because you know that when I go ask for the count of people on the planet for my database query, it's never 64 billion or 2 to the 64 people. I cannot get that many people back from the database. So there's never an overflow when I add or subtract people from a set of people. And why the hell do I have to annotate every +1 on a person count? Right?
So if I have Henry-Milner annotating my return types, in theory, it could throw in, here is everything that can possibly be thrown within this function as part of that type.
Yeah, this is how you take your map your types to.
So if I want to have a rule that's just main can't throw, when I write my main function, maybe I'm forced to either say this is a main that returns throwable or a main that does not return a throwable.
Right.
And if my main doesn't return throwable, then I have to have caught all of those errors somewhere.
Yes, you could do that.
And that's probably lighter than a language that says you have to handle the wrapping every single time, but safer than the thing that just lets you at runtime explode, because it's going to get mad at you if it says, hey, this particular, you did some wraparound math thing, bubbled all the way up to main and killed your program, like handle it somewhere.
So the sort of obvious way you would do that is you would define the return of various things would be a non-throwing integer, except add would return a throw, because add might overflow. So as soon as you use add, you're overflowing.
Right, add would return a throw. And at some point when I annotate my function as at this level of the stack, there may be no more throws.
Right. Now the reporting in Hindley-Milner is often ugly, because he gets an error when he unifies a non-throwing result with a throwing result and says, this is incompatible, I have an error now. They're not necessarily at the add or at the top level main. So you would get an error, but it might not be where you want it. A lot of work has gone into trying to get those errors where you want them, but they're not necessarily.
You could probably get away with annotating. If you annotate something, then you want to be checking. If you don't annotating, then not. But then comes the question, when you mix them, checking and non-checking, how
every time you mix checking and non-checking, you have to make a decision.
One consideration, I would consider not necessarily throwing this all into one type system. So you can have one type system that says you have an int, you have a double, you have a string, whatever, and you run your unification algorithm on this. Whereas consider wraparound or overflow as an effect. It could be that your integer addition has an effect or it doesn't have an effect, and you track those effects in your effect systems completely separately and completely independently of your types.
But that's put a strain on the syntactic side. You have to designate what do you want.
It adds a whole effect system.
Well, you can still infer. I mean, you can just infer effects just like you infer types.
Okay, if it doesn't have a syntactic designation, then do not infer checking for overflow.
No. If it doesn't have one and you're doing inference, then you allow it to discover what it is. Well,
or you annotate at some point in your program, and then you just propagate through the entire program elsewhere.
That's entirely different thing with the propagation. Yes, so.
I mean, inference can propagate. That's exactly one and the same.
To discover, do you have a chain of call? You have to analyze all the chain of the call functions, which calls one another in order to.
Of course. Every single type signature of a function also has to be annotated. So you have, just like you have a type environment when you track all of those things like double type, int, or whatever, and you unify them, you have also effect environment. And you work on the effect environment. That's plots for the function entries as well.
That is the new hotkey on the block, inferring in this kind of stuff in effects. So yes. This is active.
But it may be simpler. I mean, sometimes modularity and separating things into two smaller buckets is easier than having one very complex bucket, is all I'm saying.
Of course, it's the more powerful thing, but I personally don't think
I emphasize not more powerful. I emphasize quite possibly simpler to implement for the compiler writer and quite possibly simpler to reason about for the end user programmer. I wouldn't say it's more complex, and I wouldn't actually emphasize power as the main selling point. I would emphasize simplicity, modularity, and orthogonality.
Yeah, usability.
I mean power as simplicity. So
because I definitely have those moments where I'm writing some Rust and I'm annoyed at the thing it makes me handle, because I just want to like get my idea down and not be like, oh, here's how you handle the wrapping case. That's not what I'm thinking about right now.
Right.
And on the flip side, I get annoyed at JavaScript when I get these runtime errors that are like, you passed in a thing that didn't even have the field in it that you needed to call, was clearly wrong.
Right.
Type checker would have told you about that.
Function is not a null or whatever it is, or some common error that meant that you called something it wasn't a function, and that's not very helpful.
Right. So it's nice to have that moment where like I annotate main and be like, here are the things for which main is allowed to crash. Out of memory? Yeah, fine. I'm not going to do anything with out of memory.
Yeah.
Integer wraparound? No, my main should never be crashing because of integer wraparound. I should either be handling or ignoring that.
Yeah. That is the capability path. So you have the capability to throw a certain kind of an exception, and you have to handle it. If you don't have that capability, then no.
So Manas asked a question in the chat, which I'm going to answer. So the classic, as taught in theory in your college course, is you just crash from the first time you get a unification error. People who do Hindley-Milner for money or for serious, for production use, have much better error reporting. What I've done with AA, and it shows up in my type variable implementation here, is that I will accumulate Hindley-Milner errors until the end and report them all at once with an effort made to report where they came from. And collecting Hindley-Milner errors is a different thing. And that gives me a new kind of a type variable, or a structural type, not a type variable, structural type, the error type. And he has one instance of every possible basic type and structural recursive type. And if you unify two things that are not unifiable, you'll get an error, and he'll have them both as parts inside of him, but you now have an error type which will successfully unify with anything and everything, and he'll just accumulate all the different parts, and in the end he'll say, well, somewhere in the middle of a unifications process, everything else went except you unified this function and this int, and maybe some other things you also unified a string in with that, and I don't know what the hell. So I don't die immediately. I'll run the unification to the end, and I will get a single common unified best type, but it will include an error type inside of it.
And similar for Haskell, that GHC also runs to the end, and at the very end you may have failed to unify some of the type variables, so you end up with the so-called residual set of constraints, and then you report what was wrong. The advantage of this is that you have already done all the substitutions that you have done. So maybe if you had a function that was going from A to B to C, and you substitute A with int and C with string, then you already say, oh, you have this function from int something to string, and I just couldn't substitute something, so the user has a better idea of what the actual error was. It's more concrete in the physical code kind of sense.
Yeah.
So I think it's the only way to go to do it at the end if you want to have sensible error messages.
I threw up an example which uses polymorphism in a real way with names that are suggestive, but it's not super simple and there are no slides, so I can go through it or not. This is for Theodore here.
Go.
Yeah. So map is a function that takes a function. It's not the map call you're thinking of. This is a stupid map. And what map does is he returns me a function which just is going to apply my function to whatever argument comes to the inside. So it's kind of a dumb thing. At some point I wanted to
is an anonymous function. The inner is a definition.
Inner is an anonymous function.
Okay.
Hindley-Milner never puts names on any functions.
Okay,
So when I was calling them out and reporting what they looked like, I gave you a number. It's lambda number 4, lambda number 5, lambda number 17. No names. The name has come from the let. Let map is equal to, well, let says map could be anything you assign it to. It could be 17 or pi or string or a function. But the function's not named. Functions are always anonymous here.
Yep.
Okay.
This is the identifier for the function.
Yeah, it's the identifier. Map is just the identifier. And I use map twice past the definition. So the definition just runs to here. Then I use it twice. One time I handed a function. It must be past a function because fun is used in the function application position. I'm calling function. So function had better be a function, which takes one argument x.
Yeah.
Okay, but what
So-
is it? What is x? What is the type of the function? Well, here, this is a function where x is an int. And here, this is a function where p is a pair or a tuple. And I'm going to pull out the 0 slot. I'm taking the first element out. So one time the function I pass in is a function of an int. I'm going to return me an int, add 1 to it. One time I'm going to take a function that's going to take in a tuple. It's going to return me the first element out of the tuple. So I get two different, map is used in two different contexts, has two different types. One is map is a function which takes a function to an int, and one is a function that takes a tuple to a field of a tuple. Blah. Okay. So then I have a large AST printed out in one line. I probably somewhere in the universe have a pretty printer that does it indented to be way the hell easier to read. I don't remember now. I'm going to look for just a second. Let's see if I have an indenting pretty printer. These two strings are so the debugger can throw them out in one line, so I can look at it in the debugger. But they're not nice to look at. I thought some of these guys I put in pretty printers. That's my parse debugger syntax. Do you not have a pretty printer? Eval print for the debugger. No, of course not. No, this one doesn't have. Sorry, I don't have a indenting one on this particular set. I have a whole nother implementation which has even more robust, aggressive type things going on. That's more recent and has pretty printers.
So how your definition of map here, how your type system decides that it's polymorphic?
Right. So map. So root has an $exe let, has a let of map. Map is defined to be something, and then there's a body. So map is oh, I hadn't done typing yet. Let me go run the typing. Okay. So the overall let is the return result, which is itself a pair of an int and a field that I passed in, which I believe is going to be a 3 if I look at my dude here. Yes, the first element here is a 3. So I strongly type this as saying I have a pair of a 5 plus 1 and a 3. So
of a two application of the map function.
Yeah, let's go drill in here. Okay, so map is defined. So here's the key trick here is, okay, this is ugly because it has too many parts to it, but I can you're only interested in one of the parts. So map, and I'm drilling in. Come on, give me the wider screen here. There's an argument's passed in. It takes a function which has one argument, an untyped leaf, and returns one argument, an untyped leaf. Fun is known to be a function, but it has no constraints on it. This is the definition for map. Map will be used in contexts where a function is defined more strongly. But the map itself takes a function of any to any.
How do you deal with the
yeah, okay.
With the variation, with the
yeah, right. Okay. So this is the definition of map as used by the let.
With variance, how do you do with variance?
The variance is coming up. And the variance happens when you use the identifier map in the body of the let, and he makes a fresh copy of this. So he's going to say, you need a fresh copy of this function. And that fresh copy gets bound. Now, the map, while he takes this function, his return is a function which returns, which takes the first argument and returns the second argument.
Yeah.
So these two functions, v530 and v527, they show up in the type of map. They show up in the return per map. Okay, so that's map, which is just a function from any to any, and it takes an any and returns that the return of the function. Let's look at the body here where you start applying it. Okay, the first thing is apply is a pair of what's. Well, there are two things that go drill in. The first guy, it's an apply, which itself is going to hand a 5 and a function, and the function is an apply of map. And map says, oh, I'm handing in a function, which is going to, if you read it there, it's going to be x plus 1. Okay, so what is map here? Map, the identifier map, gets typed something that's not function from A to B. It's this horrific thing, which has been, if you step to the right of the lambda and get rid of the extra right arrows, it's my cannot unify int in 64 because I have my primitives wrapped or not wrapped because I made a change elsewhere. So this guy's reporting me an error. But if I had the integers wrapped and not correctly, it would actually be
integer,
right? Or 5 and int.
So for our viewers here, the first part is the definition of a map as a polymorphic function, and the second part is where you apply the polymorphic map is when the types are getting instantiated. So the second part is where the types got figured out to their concrete counterparts.
Yeah, this is a little complicated. Hey, CMNS, a little complicated here. I'm looking at an identifier. I'm walking the AST up here, walk AST, walk AST, walk AST, walk AST, find map. That's a pretty print of the map. The name is map. What's the type of the map? Now I'm in the type structures. Now I'm going to walk type structures, not AST. Walking this AST, he says he is a lambda function type. Map is a function type. It takes a function, it's going to return something. Okay, so that means his args take a function, that's argument number 4, that's the first real argument. 0 through 3 are my internal, 1 through 3 are my first internals, and I'm going to return something which is also a function.
Okay, here is a tricky one. At what point map does typed as a polymorphic function? So
right. So as soon as I'm at the identifier, this point, when I walk the AST and I do the Hindley-Milner algorithm, I ask the question, Mr. AST node, what are you? He says, I'm an identifier. Okay, Mr. Identifier, are you from inside of a letrec? Find the definition. Find your definition. Find map. Walk the AST up looking for map. I walk, and I'm here. I'm going to highlight AST nodes. My identifier. I walk up. Well, I'm inside of an apply. Apply doesn't make any new definitions, so map's not defined here. Walking in. Oh, I'm inside a second apply. No new definitions. Map's not defined here. I'm inside a third apply as an argument to the pair. No definitions. I'm inside this let def. I'm inside the body. I'm in the second half. I'm past the semicolon. I'm in the body of the let. It is, in fact, defining map. I'm in the body. Therefore, I want a fresh copy of whatever type. And then I unify from there. So I get the fresh type.
Why do you decide to fresh copy for a polymorphic and not for
fresh test? Is fresh just yes? I make a fresh copy of whatever this type is. And that's a type that is a function that takes a function from A to B, and then he applies A and returns the B.
So the correct term here is that the map is discovered to be polymorphic.
The map is discovered to be polymorphic.
That is the only principal type that can be given to map. So this program, the whole program, can be typed.
One of the funny things that bit me for a long time was recognizing that map's type only depends on the def, never on the body. And so it doesn't matter where I apply map because the map's def doesn't care what the body is. So all the uses of map outside, they make no change to what map's type is. That one bit me for a while before my intuition kicked in. Map is solely dependent, his type is solely dependent on his def.
Yeah. So as you say, if you try to lock it from line 11 to line 10, and suddenly the only type that would fit the principal type, as it's called, to be the map to be from A to B, from alpha to beta, if you have your type variables as a Greek letters. So this means that map can be only polymorphic for this whole program to be typed. So that is the
right. This one demands map take a function that has a tuple. Take a function which takes a tuple. This one map demands a function which takes an int. So these are two different types for map. Map takes a function, takes an int. Map takes a function, takes a tuple. Two different types.
So
it has to be polymorphic.
that was my tricky, not so
Yeah.
tricky question. Yeah.
Yeah. Okay.
So yeah, one thing key to be said here is that Hindley-Milner supports as what it's called a top polymorphism, where the A or the unbound variable is at the top of the expression. That kind of distinguish system F from Hindley-Milner, and that is why Hindley-Milner supports a restrictive set of polymorphism, not the polymorphism in its whole glory.
I am not familiar enough with what System F does to draw.
System F allows you to define an exist. We have to delve into the logic operators, the quantification. It defines to define an exist or a for all anywhere in the expression. That complicates it a whole lot. Here, if you have one abstract type parameter for the polymorphism, it has to be at the top level, at the very beginning, if you will. It cannot be nested. You cannot have a nested polymorphism. At least
I'm not clear on what you're trying to say. And I don't have the slides to go through. I clearly have types which have type variables nested deep inside them. I also have types which are fully cyclic, which means they have themselves nested inside themselves. And I get that out of Hindley-Milner with the minor extension for handling cyclic types. And I wouldn't say that that's System F.
So I will have to double check, because you have for sure problem when you have to infer a situation where two or more polymorphic functions are involved to decide what the type should be.
Okay, I hear you, but like I said, I do that naturally, comes straight out of Hindley-Milner. I don't think of anything special. So they have a name. I think we have I don't think you're wrong. I don't think I'm wrong. I think we have a name.
So I could be wrong, of course. That is my understanding of this matter. So
I mean, I can pull up. I have my is even is odd test case here, and it works just fine. And it infers that is even, depends on the type for is odd, and is odd depends on the type for is even. They're mutually recursive. Fine, it works out.
Okay, cool.
But I know that that's like the people who do System F very clearly are doing something different, and what I just described was fairly obviously well known to Hindley-Milner. So there's something different going on here. So we're missing the key piece between System F and Hindley-Milner yet. And it could just, like I said, we got jargon problems here.
Yeah.
Well, let me, we're winding down. This is like a pretty heavy one here. Let me stop sharing and claim that some few weeks from now, I should put together some slides.
Yeah, Matt throw something.
That cover both the walk to AST and Unify, and also the let polymorphism, which are both big pieces that I didn't get to. And then maybe I can figure out what System F is doing that's different than Hindley-Milner. All right.
Throwing the link, but basically Hindley-Milner is a restriction of System F.
Right, I totally believe that. And I've done extensions to Hindley-Milner, but I don't think I did them in the direction System F went. So there's yet another way to extend Hindley-Milner.
It's basically a type of functions at the type level. That is the inclusion.
Functions at the type level.
Yeah.
I've certainly seen techniques used when you want to describe type variables because you want to add type annotations. That the suggestion is you use the same syntax for your type variables as you use for your values. But that doesn't seem.
That needs to be, one is at the term level, the other is the type level.
Yeah, so
okay. A function is only at the term level. That function.
You have a function of types somehow.
Yeah.
And what kind of operators do you do on types? Sorry, don't do that. That doesn't sound like that fits in the last few minutes.
Yeah.
That sounds like a great discussion for another day.
Yeah.
Can you use this example on Stack Overflow, Steve?
Yes, Stack Overflow links are good.
Try looking at this example in the first answer in Stack Overflow, where it mentions that Hindley-Milner does not support higher rank polymorphic types.
Yeah.
And here's this here's this function f that takes polymorphic identity and returns a pair of int and string. Does this one work with
the type as listed in the example, I am certain I'll type and give you a cyclic type. Now, is that what System F gives you? And is that the best kind of type you can do? Anything that involves any set of lambdas and identifiers, I'll type with I claim is Hindley-Milner plus a cyclic support for cyclic types.
A function of the type level would count as a type constructor.
Yeah, I said that, and long time ago, Alan Gartner, who's not on now, gave me an example where I didn't minimize my result. And I didn't have a good way to get a minimization out of it. So I'll backtrack on that. I'll claim there is something that I can't do. And Alan pulled it out at least once. And I came up with a type for him, but it wasn't the type you expected because I didn't minimize.
It must be because, I mean, System F is proven to be undecidable. So there must be some cases that it will not be possible to
Will not be possible. Okay. Yeah, you know, in 10 minutes, which I don't want to do while everyone's waiting here, I could throw that example into my type guy and ask for what he does. And, you know, I cannot imagine he'll crash, but I can imagine he'll hand me some weird cyclic type that may not be something that you're excited about. Because, like I said, because my algorithm, I know my algorithm I know my algorithm terminates, and I know I handle cycles. I don't die on cyclic types.
Maybe we're missing something here, but
yeah, boy, I'm really excited to go do this example because it's really small, but I can't do it like fast because I'm not set up for it doing it fast here. I need get into the test directory. I need to find my test harness. Test tvar. I have a bunch of tests in here. I don't have a good harness. I don't have a good jig. I'd have to go build the type up with a bunch of manual code. All right, I'm not going to do it now. This
Can you type? Can you type a polymorphic self-application to a self-application? That's the Stanford example.
Right. Let me.
So you take a function that takes anything, and then it happens to take itself, and it applies itself to itself, and it's polymorphic.
Yeah. I have that example. I have.
So you don't have for all XX to for all XX.
I don't have any for alls because I don't know what they mean. So we have a name problem with for alls. I don't use for alls or there exists.
Placeholder to placeholder in a sense.
So the polymorphic type A to B. So A should be, if you don't have an A in your program, that should be interpreted as a for all. So the map is a for all A to for all B, for example, the map function. So abstract type A to abstract type.
Okay.
So you have a lambda that takes an X.
Yeah.
And then it applies X to X. What is the type of this lambda in your language?
I'm looking for my example. I have that in my examples. It is the function that takes X and returns X, and it comes out of the typing system. And I'm not finding.
No, not takes returns X. It's a function that takes X, and then it's applying X to X.
Yes, and it returns nothing. It returns the free variable because you never return from that. I don't have it. Damn it, I can't find the exact. I have an obvious test case, and I'm going to have to pull it out. Okay, let me look in the other directory and see if I can't find the self-cycle type here. Oh, it's in this one.
In System F, you're still going to have the resulting type that it's a function. It's going to be a function from a polymorphic type to a polymorphic result.
Yeah, it's polymorphic.
Polymorphic to polymorphic.
Yeah.
Boy, let me try a grep over.
I forgot about that. Identity example. Yes.
That's for. I'm doing it for structs too. Oh, yeah. Okay, I don't have it lying around, but hang on. This is one I've had it lying around. So let me instead go make it. And we'll see if we can agree on what it is. So f is a function which applies itself to itself. And now I don't have the type for that till I run it. Let me go. What did I call it? Test recur 17. I'm not screen sharing. Well, you don't see me crash on board here. Okay, so I got a type.
Which is?
And it's the very boring type of itself to itself. Yeah. Okay, so let me make sure we're on the same page here. Share, blah, blah, blah. Back it goes. Too many things. Test recur 17. Okay, so this so ignore the types out here. This is incorrect. I just cut and paste. So f is a function which takes an argument x probably, and I want to apply x to x.
X to X, yes.
Is that a better?
Yeah.
Okay. Yes. So that types. No, it doesn't. Test lacks a file marker. Oh, come on. Okay, I need doesn't type because I undid my hang on. Oh, I put it in. I was doing it in. Oh goddamn, too many windows now. Doing it here. Come back to here. He wants a test harness demands a type. It's the wrong type. Those types do not make sense here. So ignore them. See if I get past the test harness.
One example, try also applying this function to identity. So also what is your type when you apply f to identity function?
Right. Okay. So let me claim that I get a type here, which is a lambda. And if you ignore things, it takes a function which is itself. So the e colon right here, my cursor is right on e colon. You can see my cursor. That says I'm about to define a type which is cyclic, and e will appear later on in this expression. I'm about to reuse the type for e. So it's a lambda whose first row arguments, ignore the underscores. Those are dummy arguments for extensions. Okay, the first row argument is e. He takes himself. He has a function which takes himself as this first argument and returns a free variable, a leaf which is untyped. That's his type. Takes himself and returns a free variable because he never returns, so there's no binding, there's no constraint on what the return type is.
Can you apply it?
It's good. Try applying this to identity. I'm curious.
So now let's apply it to identity.
So define identity function just takes x to x.
Yes, it is equal to y arrow y.
You are not sharing the screen, by the way, with the example.
Oh, I'm typing. I'm sorry. I'm typing an Emacs. Let's go back to.
Fair enough. Fair enough.
Here, I'm not yet done. Okay, so now
and I want to apply this function to identity. Yeah. And what type are we gonna get?
Better put a semicolon here. Well, you know. Okay, I got a type. Didn't get a crash. He says I get this type. Okay, what's this type? Some lambda. And there's a lot of repeats on the D here. D is, so he says my type is it's a function that takes a function which is his own type. He takes himself as his first argument. And that's himself again then. And he's returning himself. 532 has been forwarded to union find to the same thing. So the debugger says at 1669, that's the same thing. So he takes himself and returns himself.
So it is a polymorphic identity, right?
Yeah.
Okay, that's also what you get in systemf.
Okay.
When you apply the self-application function to polymorphic identity, you get polymorphic identity. So this you are getting the same result.
Right. Now I don't claim I'm doing systemf. I have no idea. All I claim I'm doing here is I handle cycles and the types. And one of my first slides up, I said, and maybe some graph theory. And what I did is at some point I recognized these types form a directed acyclic graph from a DAG. And they fail when you say, hey, I have an occurs check fails. But that would otherwise make a cycle. Well, I'm a compiler guy. I know how to handle cycles. So I'll just handle cycles. So I just handled cycles. And then I get these types. If you do these kinds of things, and I get a type out. It doesn't fail. I get a cycle. So everywhere my algorithms have fancy bits that say, I handle cycles here. And all of the unification steps and the cloning the graph handles a cycle. So it clones with cycles in the graph and all, but it's all just cycles. And I do graph operations and nothing with types, right? I said, all your types are represented as a graph. Okay, I have a graph now. Ignore the type semantics and the type this. It's just a graph. What do I do with a graph? I do graph things. Fine.
Which is nice because I like linked lists.
I'm sorry. Yeah.
I said, which is nice because I like linked lists.
Well, this is a graph of types, but the types can have, you can do linked list. I can infer linked lists directly. I've done that.
I was just thinking that a lot of my tree algorithms are, and then the left is a me and the right is a me.
Yeah.
Linked list polymorphically. I remember that we have at least done it 5 times. So
yeah, I've done it a bunch. This has been working for a while.
So this should be some kind of higher rank polymorphism for sure.
Okay, if somebody not me says it's a higher branded polymorphism, I'll take it. But I can't say that. That's not my skill set.
Yeah.
I mean, the higher rank comes from the fact that your f function was taking a polymorphic type and it was returning a polymorphic type. And that's why you could apply it to identity, because identity is a polymorphic type. You took that as an input, and then you return identity as an output. So you return the polymorphic type.
Yeah, but in common, I mean, Hindley-Milner everywhere, the standard one takes polymorphic functions in and returns polymorphic functions. You're saying it takes...
No, Hindley-Milner cannot do this.
Well, this one here you can't because he hits the occurs check and chose.
It's essentially once you set the once you apply this, once you instantiate this polymorphic type once, you are done with Hindley-Milner. So the point is that it's really hard to explain this without using the for all quantifier, but you can use the for all quantifier. Come on, I mean, identity function basically says that for all A, return A. You get it, right? So if you take it an int, it returns an int. If you give it a double, it returns a double, right?
Right.
So that means that for all types, it returns the same type. Yes. Whereas, and that's what you can do in Hindley-Milner. You can only put this for all in the beginning. So once you decide it's an int, you're gonna be returning an int.
Yes.
But in system F, you can keep putting this for all, also, for example, in your return type. So even though your input has been inferred and decided, you can still return some bit polymorphic, and that's only going to be decided later on, whatever it is you unify with, for example. And that you cannot do in Hindley-Milner standard.
Yeah, that was what it counts as a top level polymorphism. That is Hindley-Milner.
So essentially, I don't know that we're speaking the same language still, but essentially my type is a function type which takes itself as a function type and returns itself as a function type.
And the same D, yeah.
Yes,
but in system F, you could return suddenly some unrelated E, and that unrelated E would also be polymorphic. And it would have nothing to do with D. It wouldn't have to be constrained to do with D.
So this is not system F, because what you said was it does this.
Yeah, that could be completely, maybe that could be another, this type itself may be polymorphic. So it could also take some polymorphic function to some polymorphic function.
As soon as I say in E, I say type variable, it's polymorphic. But I don't have it. I am binding the return to D and not to a free variable, a free type variable.
Yes.
So that's the difference. Yeah, because in Hindley-Milner, you're done. You once you have D, you have a D, but in system F, you can continue with the polymorphism.
You have to instantiate. You cannot return.
Yes. That makes more sense to me than claiming that somehow closing a cycle gave me system F. I wasn't believing that.
Yeah.
Fine. All right, now I do want to break.
Yeah.
And besides lunch, I owe people other things I need to go do. And then there's slides, or not the slides. Oh, fine. Well, I'm going to claim, victory for the alliance here. Somebody else on chat probably saying they got to go. Yeah, got to go. Okay, fine. Yeah, it's late. Yeah, we're down to like 5 people now.
Hmm.
All right. Well, till next time.
Have a good weekend.
All right.
Yeah.
Bye-bye.